Good morning and good afternoon, depends on the time location that you are now. Um, Welcome to this lecture where we will go through the support vector machines and also the kernel machines. We will see in this lecture that how to deal with some of the most famous machine learning algorithms, which simplify the analysis, mainly in classification, but also in regression as well. Support vector machines actually makes the problem or simplify the problem of classification, where we don't need to model the data, uh, building some statistical model of the data, or looking for the probability density function of the data. And instead of that, we start to look or to model the boundaries between data that we have for the purpose of a classification, and later we will see for the purpose of regression. So this lecture is important because it presented the problem from different angle point of view, and we can see that this simplification will not damage or destroy the efficiency and the quality of this classifier. It works fine in many cases. Because of that, it has many different applications in literature. So if you go to literature and just search about using support vector machines, kernel algorithms, you will find like tens of thousands of publications where these techniques was very successful. And it has actually many features. For example, the problem is convex, linear. It is linear algorithm, and it is also convex. The convexity here means that we have a single and optimal global optimal solution. So we don't have the problems, for example, of deep learning, where we can stuck in local minima or in saddle point, which does not achieve the required performance. In the support vector machine, because it is a linear technique, so it is convex, so we have single solution, and this solution is a global minimum. Okay. There are other features actually for the support vector machine. For example, if we have a huge data, the problem is reduced to have a few samples of this data, which represent the support vectors, as we will see. However, again, we are not going to explain the whole lecture slide by slide. It is already recorded, but let us go together to see the general concept and the main concept of support vector machine and how it works. So let me start by sharing the lecture, the slides. Yeah. So as you can see here, we start by the definition of kernelization. What it means? It means that we reduce the problem, and we get some the optimization problem becomes much easier when you deal with reduced size of the problem. And then we have some just introduction about linear discrimination algorithm. It is, of course, supervised learning algorithm, this support vector machine, as we will see. And the idea, as I said, that we don't need um, to model all data that we have, because we are interested mainly in the boundary between both classes. Okay, so what I mean here, so this is what I will go to now to the whiteboard to see what what is the concept of support vector machines? So assume that we have a two-dimensional problem with two classes. Okay, so we have two-dimensional x1 and x2, and also we have two classes c1 and c2. Okay, so this is c1 class, and then we have a c2 class. Maybe we put it as a star like this. Okay, so now we have uh, the problem is represented by these values. This is in your supervised learning because it is labeled. Okay, we will start with very simple case where it is linearly separable problem. So we have something like that. Okay, so now we have such kind of data where we have class 1 and class 2. In the parametric classification that we studied before, or also in the whatever technique that we have seen before, all those techniques were considering the representation or the modeling of each class. So we come to class 1, we compute from class 1, we compute, for example, what is the distribution or what is the probability of being class 1 given that you have this data. And in order to find this, we need to build the discriminant function, which is like the distribution of x given the class that you have multiplied by, sorry, the probability of the class, by the probability divided by the evidence, which is the joint distribution between all instances. Okay, um, we used this before. We saw different techniques actually to do that. We can do it also with the neural network. So in a neural network, for example, then we have, this is the neural network, we have the inputs, in this case x1 and x2, and then we have the output, and the output we put it, for example, as 1 for c1 and -1 for c2, for example. Or we can have two outputs where we have like 1 0 for class 1 and 0 1 for class 2, or whatever technique that we have seen before. And in order to make this learning, or in order to build this discriminant function, we need to use all available data. We need to use all available data. Assume here that in class 1, we have, let's say, 10,000 elements. And in class 2, let's say that we have maybe 8,000 elements. Okay, so it means that totally we have 18,000 elements. We need to go through those 18,000 elements in order to build the discriminant function, which could work, which could learn the data, where when we have a new input, a new x1 and x2, when we have a new x1 and x2, then we can use the learned data in order to classify the new data, which is it belongs to x1 or belongs to x2. I just remind you that what you see now on the whiteboard is very simple case where we assume only two-dimensional problem. In reality, we don't have such kind of, because such kind of problem actually it can be solved by just by looking to the problem. But in reality, you have many higher dimensional problem. Maybe you have hundreds of dimensions of the problem. Maybe you have thousands of dimensions of the problem. Okay, and also you have tens of thousands of data instances. So it is not possible to visualize them in this nice way. Most of the problems. Okay, so just remember that. Um, the support vector machine is based on very intuitive and simple like concept. What is this concept? The concept is that the classification is based on the boundary between those instances. Where is the boundary? We can put the boundary in between these two classes, which is this one. This is the boundary between these two classes, for example. Okay, so this is the boundary which classifies between C1 in one direction and C2 in the other direction. Okay. Is there any impact for, let's say, for example, for this instance, xi star, does this instance has any impact on the boundary? No, because this instance is already far away from the boundary. So actually this instance will not have any impact on the shape of the hyperplane which classifies between those two classes. The same concept is, for example, for this instance. If we look to this instance or this input, doesn't have any impact on the shape of the boundary between two classes. From this basic and intuitive concept, the question arises now, why should I model all this data or all this data in order to build the classification? Which looks actually very correct and very intuitive question actually. Why I need to compute this one and this one, the effect of all this data once it doesn't have impact on the shape of the hyperplane between the two classes? Actually, for example, for me now, when I was drawing this problem now on the whiteboard, when I draw this line between these two classes, I considering only to be in between the boundary instances. So I took into account during drawing this line, I took into account this one, for example, this one, this one, this one, and maybe this one as well. So those are what I considered when I make my, maybe there's one here, when I make this boundary. And also on the other side, I took into account maybe this one, okay, and maybe this one, I take into account, I took into account this one and this one. So those are the instances that I considered when I decided to draw the hyperplane between those two classes. Then when I optimize and I want to find the optimum classifier between two classes, I should build equation which considering only the support vectors. What are the support vectors? Those are the support vectors. The support vectors are the vectors which determine the shape of the hyperplane. Those are called support vectors. Actually, this is very interesting result. Very interesting result because of many reasons. One reason that in this case you might have like let's say 20,000 instances input, and you find that your support vector which determine the shape may be less than 20 instances only. So you build your vector, or you compute only 20 instances. You take into account only 20 instead of 20,000. So can you see how much computation power that you reduced, and also how much the problem becomes even more like obvious. And because usually when we build this hyperplane is built based on the instances themselves. So it is weighted, the weight itself of this hyperplane is based on the instances, which makes it easier to interpret, to visualize, and also much faster to compute, and also very effective way for the classification. In the lecture, we started by linear hyperplane, by assuming that it is linear, not in the shape that you see now. It is like curved. But after that, we extended to nonlinear case by using the kernel. So we can use different kernels in order to build any shape or most of the shapes that available that we can use. I saw some publications what published like several years ago, where they also try to find or to emulate actually the deep learning and neural networks by using this kernelized support vector machine. Because in the kernel of the support vector machine, you can use sigmoidal function in the same way that we use in neural networks. And then they try to show that it could be like compared to each other, and the support vector machine can be seen as a generalized algorithm for many other algorithms. So, for example, if it is linear or nonlinear. And again, the nice thing here that you don't need to use all your data. You don't need to use all images. For example, if you are classifying between images, so you don't need to use all images. For example, if you want to build the differentiation or the classification between the images of dogs and cats, there are some pictures which are clearly for dogs, and there are some pictures they are clearly for cats. Okay, so they are somewhere here, far away from the border. But where we should put the optimum border between these two pictures, we should put them where the pictures, they are hard to classify, they are very close to each other. Then this is the border there where the border should be. So this is the main concept, the foundation of the support vector machines. Okay. Let us go back to the slide. Okay. Yes. So sorry. As I said, so one way or the simple way is to start with using the linear discriminators. But remember that not necessarily that every problem is linearly separable. So this one, it will work if the problem by itself is linearly separable. Okay, so in this case we can use linear hyperplane, and in this case we can assume that our discriminator function can be represented in this way. So it is the weight, okay, transpose times the instance x. So the weight, it will have the same dimension of the dimension of the data itself. So if the data is 2 dimension, then this weight will be also 2. If the dimension of the data is 1000, then of course the weight will be also 1000. We take the transpose because the result will be scalar. So this will be 1 by d, and this will be d by 1. When you multiply them together, you will get a scalar, or you get a single number. And then this will be the drift of the linear equation. So this is the idea. Now our question is, what is the optimum wi and this drift? What are the optimal one to separate between between both classes. Okay, the way that we compute the optimization, it is clearly shown in the recorded lecture. But here I will also mention one thing more in the white board. So in the whiteboard, I will just again assume that the function is second order again. Okay, so it is x1 and x2, as you can see. Then the data, we assume that the data is linearly separable data, not as the previous one. Okay, so just assume that the data in this way, and also the other data is something here. Okay, so our question now is how to find this W1, and because the data now is two-dimension, so we are looking for the W1 and W2, the weight vector W, which is vector of W1 and W2, and also W0, in order that we can classify between between these two classes efficiently. So actually, based on W1 and W2, you can have different kind of lines. So the line can be something like that, or it can be something like that, or it can be something like that. Can be any line, depends on W1, W2, and W0. Okay, so in support vector machine, we approve that the optimum W1 and W2 is computed or will be computed based on the data itself. So it will be something related to the support vectors, which will be something like W bold, which means that it is W1 and W2. It will be like summation of alpha I, for example, times xi. And xi is also like x1 and x2. It is also two-dimension as well. And then it will be multiplied by alpha. Alpha is greater than 0. Alpha is related to the Lagrangian multiplier. Okay, it was explained before but I will not go back to it now, but it is already in the recorded lecture. So now we can see that this W is computed based on the instance, but which instances that it will be included, it has been approved that only the instances which are very close to the boundary, which will be this one, this one, this one, this one, and this one, and also maybe this one, and this one, and this one. Those will be included in the computation. For all the others, will be 0. Even if you remove them from the data set, they will not affect your boundary properties, because the boundary properties depends on those vectors or those instances which are very close to this boundary between those two classes. Okay, and this is in the case of linear. Okay, but what if the data are not is still linear, but is not very very good separable or separated in very good way? What I mean, assume this case now that we have this case, this vector. Okay, which have well, I have one class now, and then we have another class, maybe something here. Okay. And maybe we have some points here as well. Actually, this looks more practical situation where we don't have very nice way classified data. It is still linear, as you can see, they are linear, but we will not have like exact line. Whatever your optimization that you use, as far as you want to use linear classifier, there is no single line which will separate between these two classes. However, the both classes looks separable, because if you go outside this region, you can see that it is very nice separated outside this region. Okay, so in this case we will try to find the best linear separable function which will minimize the misclassification between data. So we try to find the best line, which can be something, for example, here I can use different color for this, maybe. So I try to find some line, maybe something like that. Okay, so this line which will minimize, now I am not looking for perfectly separating between classes, but I am looking for the line which will minimize the misclassification. What is the meaning of misclassification? Is the instance which comes to the other direction. For example, this one is misclassified because this one, it should be in class 2, but now it came to class 1, but I cannot do anything for that, because as far as I want to use linear classifier, then I need to accept a few cases which will be like misclassified. As far as those misclassified instances are very small, for example 1 per 1,000 or something like that, maybe we accept that. And actually we might have some like physical or some justification for that. For example, in some diseases, based on the features, it is very hard to be classified based on the symptoms. And even the most expert professors in the area of medicine, maybe he or she can make mistake, because those symptoms are very close to be, and extremely close to be, the same symptoms for two separated diseases. So in this case, you cannot do anything. Okay, so our purpose now is to minimize the misclassification between those two classes. And again, we consider only those elements which are within this margin. We consider only, for example, from -1 up to +1. If this is -1 from the line up to +1 from the line, and then we try to find the optimum line which will perfectly, or at least it will minimize the misclassification between those two classes. Then in the recorded lecture, you can see the explanation how to build this one as well, and how to build also the Lagrange multiplier equation, and how to optimize it. And then, of course, all the others, these and those, will not have any effect on finding the optimum line. Only the elements which are close or around to the boundary between those two classes. In case you have multiple classes, you have, for example, 6 classes, not necessarily you have 2 classes, you might have more than 2 classes. So the idea in this case is, or the best way to do, is to divide them into like 1 against all. It means that you start with class 1 and you assume all other classes as class 2. Then you compute the best line or the best hyperplane to separate between this class and the other classes. Once you separate them, you come to the other classes. For example, now C1 and the other classes, we have the equation. Then we come to the other classes, which is C2, C3, C4. And then I take one of them, like C2, and against all the others. So C2 will be against all the other classes. And then I find the optimum line for that those classes. And then for C3, we do the same until I build the k different hyper plane equations or classifier for each class. Then when we have a new entry, I put them in every equation or in every discriminator, and then I select the one which give me or which gives me the highest output. Okay, so this is the way that we can do for the multiple classes in the support vector machine. However, I remind you that it works fine for in the way that I gave now. It works if the data is already linearly separable. But if the data is not linearly separable, then of course we need to extend this by using the same trick that we showed before. What I mean that we move from the original space of the data to higher space represented by or called as the kernel, as we will see now. It is actually based on the same idea here. We explained this before. So, for example, if you want to separate by this one-dimensional data, and now we have two classes, the star class and the circle class. There is no line that could separate between them. So if you put it here or here, so whatever you put that you cannot separate them. So the idea here is to transfer this problem into higher dimensional, where it becomes linearly separable in the higher dimension. So now in the one dimension, it is not linearly separable, but if you take the square, which means that you convert from x to x and x square. So now we have two dimension. The original problem is one dimension, but now we have two dimension. Okay, and if you take x versus x square, you will have something like that. Now this problem becomes linearly separable. This problem becomes linearly separable, and we call this as the dimension trick. So the problem in its original dimension is nonlinear, but we transfer this problem to another space. On the other space, it has usually much higher dimensionals than the original problem. Of course, in this case that we see now, between 1 to 2 is very simple situation. So now we need only to go from one dimension to two dimension. But in some other problems, maybe you need to go to much higher dimensions. For example, if the original problem is in 10 dimension, and it is not linear, it is non-linear in this original 10 dimensions. Maybe we need to go to 100 dimensional problem, or 100 dimensional space, 10 times larger dimensions. Then the problem becomes linear at that space, at that new space. Okay, so by this way, we call it as kernelization of the problem. The kernelization of the problem, as we will see later. Okay, so now we just here explain some the mathematics behind finding the optimum or the optimal hyperplane, as we explained before. Okay, as I said that it is already explained in the recorded lecture. Okay, but it is very straightforward, very easy to calculate. There is nothing special here, just simple linear optimization problem, or quadratic actually optimization problem. Yes, so this is what I mean now, or when I said that we can classify the data, and now we consider only those in this margin that they will specify the properties of the classifier, not all elements. Okay. So in the nonlinear classifier, we use the kernel trick, and the kernel trick simply is that we convert the problem from it is original dimension or it is original space to another space, and we call this by taking the phi of x. Okay, so you have then we have a new space now. It is z space. It is called Z space. Okay, and after we convert it to the Z space, we apply exactly the same equations that we have seen before. So we have the support vectors, but now the support vectors is not X. The support vectors now are Z from Z space, not from X space. After taking the projection of this X space into Z space. Then we apply the same equations. So as you can see, so we can apply exactly the same equations to build the weight, the new weight. But remember now, this new weight vector, the dimension of the new weight will be the dimension of the new space. For example, if x was 2 dimensions and we project it into 100 dimension to become linearly separable, okay, then the weight now is not 2 dimension. The weight now it becomes 100 dimension as well. Okay, and I will give you some simple example. Of course, we have different kernels that we can use, or the projection that we can use. Either we use polynomials of degree q, we can have radial basis function, and we can have also sigmoidal function. For example, in the polynomial function, it becomes in this way. So the kernel now it becomes like x transpose times x. Okay, the kernel between the kernel, actually, what is the meaning of the kernel? The kernel is some similarity measure between two vectors. Okay, so the kernel here between the instances data that you have xt and the new data that you have x vector, it becomes xt x transpose times xt plus 1. Okay, now if you have a q equal to 2, it can be 3, it can be 4, it can be the number that you want, and assume that the dimension now is 2. What is the meaning? What is the meaning of dimensions 2? That you have x1 and x2 only. You have 2 dimensions. Okay, then if here you have 2 dimensions, of course you can call them like xt and y, for example, as I did here. So I call it like x and y. Okay, so it becomes like x1 x2 transpose times y1 y2. So when you and then I take square. When you do this, you will get like here x1 times x times y1, x1 times and then x2 times y2 plus 1, all square. When you take the square of this one, it will be like x1 square y1 square plus x2 square y2 square plus 1. Then the cross multiplication, it will be x1 x2 y1 y2, and then of course it will be divided 2 times, so it will multiply by 2 and so on. So by doing this, you will get this new function now. So you can see now I have 1 2 3 4 5 6. I have 6 dimensions now. Then I can define phi x, because this is the phi, phi x transpose, and phi of y, or for any other like elements here. Okay, so now phi becomes from this equation I can decide that phi is 1 square root 2 of x1 y square root 2 of x1, because when it is multiplied by phi transpose, and phi transpose I will have also square root of 2 y1. So square root of 2 times square root of 2, it will be 2, and x1 times x2, it will be this element. And the same for every element in this equation. So now you can see that we will have now 6 dimensions. 1 2 3 4 5 6. I have 6 dimensions now. The original problem, it was 2 dimensions, but now I have 6 dimensions. If you have a q equal to 3, it will be even higher number of dimensions. Okay, it will be higher, and so on. So this is one way that if you want only to use polynomials without using other like radial basis or sigmoidal, if you want to use only polynomial, then what you can do, you can test. Again, we come to the same problem of learning, that we divide the data into training data and validation data. Okay, then I start by trying to use linear separation of your data. Assume that X that you have, it has 20 dimensions, for example. Then I build W, the weight, in the way that we showed before. Okay, and there are many ready functions that they can do this for you in Python and in MATLAB or whatever language that you use. Once I compute the optimum hyperplane for this data, I try to apply it for the validation list. If it works fine, that's great. So I don't know to go to this vectorial kernels, or make any kernelization of like using higher order of space, because it works already with the original dimension or in the original space. But if in the validation the result was bad, so it was not able to classify between them, then I need to look for higher dimension, because it looks that the problem in it is original dimension, it is not linearly separable. Remember, I repeat again, that you cannot decide that by looking, as we did in the 2 dimension, because 2 or 3 dimension we can just visualize them, but in general we cannot do that. But we can see based on the validation. If the validation didn't work as it's supposed to work, or as it should work, for example, if you put your criteria that you want in the validation, that it should work with 80%, for example, if this 80 or 85% didn't or was not possible to achieve, it means that the problem is originally is not linearly separable. Then of course you can go and apply this. Now you apply your data with the q equal to 2. So in this case, if the original problem was 10 dimension, now you get 30 dimensional problem. Okay, and with the 30 dimensional problem, you try, or you start using the data, the set of data that you have, by looking or by computing the support vectors of the data, and then you build your new weighting vector for the new data in the new dimension. Then you apply them to the validation data. So if it works fine, that's so great. If it didn't work, then you might decide to increase the polynomial. So for example, using polynomial 3 or 4, maybe you end up with, let's say, 200 dimension or 500 dimension. Of course, the problem becomes very huge in this case. And you apply it again to check if it works or not. And you continue until you get the good separation. But sometimes the polynomial, using polynomial in this way, is not effective, because the number of dimensions can increase in like accelerating in nonlinear way. So the other way of using the kernel, or the vectorial kernel, is by using radial basis function. Actually, sometimes it is called Gaussian kernel as well, because it has the same shape of the nonlinear part of the normal distribution. So we have here the norm, the norm for the basis 2 between the instances and the other data, divided by 2 s square. So s actually in Gaussian distribution represents the variance, the s square. Okay, and we can use this kernel now of the data that you apply, and then again you can compute the optimum weight as we show before. But you can see previously we compute the optimum weight as the summation of what? Summation of the support vectors of the data, as you can see here. In the new case, when we use the higher dimension, or we involve the kernel, then in this case the optimum weight, it will be based on the phi of x, in phi of x, if you want to have the optimum weight. Okay, and actually it was interesting because remember always that we are not mainly interested to finding W. Of course, finding W is essential, it is needed. But finally, I want to build the classifier. And the classifier, what you need for the classifier, once you build this W, let me go back. Sorry, reset. Yes. Once you build this W, okay, and then maybe I can write here on the board. I will try if it is possible or not. Okay, maybe then I go to the whiteboard. I try to write to the screen. So now we saw that the optimum weight is equal to some summation over the support vectors only, not all data, but only the support vectors, I equal to 1 up to the number of support vectors, maybe m or whatever. So this will be R of I. The R is if it is in the class or not in the class. Usually, if the data in the class, we put Ri equal to 1. If it is out of the class or the second class, we put Ri equal to -1. So this will be, and this multiplied by alpha I is the Lagrange multiplier, where alpha I is greater than 0 and less than or equal to C. This is actually explained in the recorded lecture, and then this multiplied by phi of x, xi, and xi are the support vectors as we saw before. Now we have this, our classification now. This is our discriminator actually, our discriminator of x. Now we have a new x, okay, equal to summation I equal to 1 to m ri alpha I. I think in the slide it was written as t, but it doesn't matter, I or t. Then multiplied by phi of xi. Okay, this will be your weight. Okay, of course, because the weight here is transpose, then this phi I would be the transpose of phi I. What is your purpose? What we built? Why we built this discriminator? Because now we have a new entry, xs, a new entry, and I want to check if this gives me greater than 1 or greater than 0 or less than 0. If it is greater than 0, it is a class 1. If it is less than 0, then a class 2. How to calculate it? I need to multiply this by j of x of our new x, which is x of s. Phi, sorry, phi. J, phi. I will write it again here to make it show. This is a j of x. This is x, which is a new xs equal to, this is the weight, ri, alpha I, phi of x. I put x as a bold because it is vector transpose Okay, and now this will be multiplied by phi of the new x. So you have a new x, and I want to check now if this one is greater than 0 or less than 0. Okay, now if you multiply this inside, what you will get? You will get summation Ri alpha I phi transpose of xi, okay, multiplied by phi of xs. This is the new x. Okay, by looking to these two, they call this as a kernel. Okay, they call these two as kernel of between your data, not all data. Remember, here you put the support vector data, only the support vectors, only the support vectors, x and xs. So maybe x here, because now you have the dimension of the new dimension of your data. Okay, you have now the new dimension of your data. But what is the elements here? The elements here will be n, because you have n instances. Okay, so by substituting instead of this, we put the kernel, and now the kernel, as we show in one example, one numerical example in the slides, so you can see how to apply it. So what you need actually, you need only to give to get this phi or alpha, the Lagrange multiplier, which are greater than 0. Okay, and then you get the classes of the support vectors, and you get the instances of the support vectors. Then you have the whole, like classifier or discriminator that you can use with any new data. And this phi times phi transpose times phi is called together is the kernel that you can use, for example, polynomial, or you can use radial basis, or you can use sigmoidal function, as we can see. Okay, so yes, you can see here that this is the phi. This is what I now was explaining. This is the transpose. Okay, of course, when you have a new instance, you must apply also the new dimension. You should remove, you should move it to your new space, new dimension. This is the reason that we take phi of x. But the nice thing that instead of going through all these details, we can put those together, phi transpose times phi, as k of x transpose and k, and we call this together as the kernel of the problem, okay, or kernel machines. Okay, so now we mentioned that this is the polynomial one, this is the radial basis function, and also we have the sigmoidal function. Sigmoidal function is very widely used. And actually here I put 2 and 1, but generally, maybe if you look to other books, you can find here like alpha and beta, or A and B. And those parameters can be tuned in order to have the best classification, the best possible classification. How could you know that you get the best or not? Again, by looking to the validation list. You start by the training list. You find the optimum, the optimal support vectors, and also the optimal Lagrange multipliers during the training. After that, you try it with the validation. And during this process, you can also change alpha and beta. Instead of using fixed 2 and 1, you can change alpha and beta, and repeat until you get the best possible result. Here we have one example. You can see about using this kernel concept. So you can see here we have two-dimensional problem, and you have this data already, where you have we have 7 data here, and we have x1, x1, and then we have the result. After making the optimization, the quadrature optimization that we saw before, then you get this Lagrange multipliers. Alpha 0.5, minus 1, minus 8, minus 3, minus 0.5, minus 9, and 3. And the penalty factor was c equal to 0.9. What penalty means, of course, you need to look to the or to watch the recorded lecture. But here we know that the support vectors alpha must be greater than 0, which means that out of all this data, we have only two support vectors, is the first one and the seventh one. Okay, so this one and the seventh one, those are only the support vectors. The others are not. So simply ignore all of them. Ignore all the others. Okay, and now they said that you have because c equal to 0.9, and we know that the maximum number that this Lagrange can take is the penalty factor, and because of that we can compute the weight in order to that it is 0.5 and 0.9, not to 3. And again, you can just go back to the recorded lecture to see why we got these values. Okay, and then we have this new 3 and minus 1. This is new input, and we want to classify it based on this calculation. So it was the example was solved here, and also there's a recording for the explaining this example is added to the model. Okay, so we can build our because it is required here that you use radial basis kernel. So now we use the radial basis kernel, and it should be multiplied by alpha transpose and RT. Alpha t here is not transpose, t here is the number of the instance, alpha t, and RT. K of xt and the new x. Okay, so alpha t here is equal to what? 0.5. Okay, and for the first one, the class was class 1. Class 1 means that r equal to 1. So it will be 0.5 times 1 is 0.5 times k, the data x1. What is x1? This one, 2, 2. What is the x? X here is the new data, which is 3 and minus 1. Okay, minus, why I put minus here? It should be plus. The reason that I put minus, because the second support vector is the seventh one, this one, and in this one it is belonging to class 2, and since it is belonging to class 2, then this r should be minus 1. So it will be minus 1 times alpha. What is alpha? Alpha here is equal to 3. But as I said, as you can see, that the maximum alpha shouldn't be more than the penalty factor c. So we take 0.9 instead of 3, becomes 0.9. And k between the seventh input instance and the new data that we have. By applying this, we got the discriminator output to be 0.0031, which is greater than 0, and then it belongs to class 1. This is the way that how the kernels and support vector machine works. Okay, this exercise here, and then we apply some also classifiers to see the differences in kernel machines. Kernel machines is one very interesting topic, and this is one of the topics where the data scientists, they try to invent sometimes new kernels based on their own data that they have. Sometimes they have data which this sigmoidal or polynomial or radial basis, they all of them, they don't work in efficient way because of the specific nature of the data in the company. Because of that, they start to invent new kernels, and the new kernels can be combination between different kernels. For example, even in the same data set, you can divide them, that you use, for example, radial basis for this data set, And then you use, for example, sigmoidal for the second data set, and use linear for the third. Even it is in the same data, but within each class, you can use different kernels. So the kernels gives you a lot of freedom and the flexibility to use. Okay, and as you can see here, for example, the kernel can any, for example, scaling of the kernel, it will be kernel. Any combination of two kernels can be applied as kernel, and any dot product between two kernels can be also kernel. So this gives you a lot of flexibility in order to work with simple the different kind of data. So you can use like for example for information fusion, if you want like sensor fusion, for example, information fusion, you can use different kinds of kernels. The topic is very wide, and also there are a lot of books and papers published in how to select the kernels and the specifications of those kernels, and how to construct kernel based on specific data that you have. But again, remember that the support vector machine is extremely important technique. It simplify the analysis, it simplify the work when you have a huge data, very large data. Then instead of looking to the everything, you just build your simple classifier, which is based on to model the boundary between those classes. It can be linear as the original support vector machine, and it can be extended to be nonlinear by using these kernel machines or kernel engineering techniques. Uh, that's all. I talked already about multi-class kernel machines, and as I said that you can solve them in the same way as we show it here, but the easiest way is to work like one versus all. So this will be more effective and faster to apply. Of course, there is also some recursion-based kernel machine, and uh, it has also some benefits, because it can remove the outliers from the data, and also it can reduce the number of data. So it is the same idea. You decide some uh, some dimension or margin, where you assume that the error is zero if your data within this margin. Okay, so you can see that if the data R here is not 1 or minus 1 in the as in the classification, R here is the real data that you have, because now you have regression, not a classification. So here is the real, for example, the prices or the weight of the person, or the price, the stock market share price, and so on. And minus f of xt if the difference is within certain range, which is divided by epsilon, then you assume the error is zero. So what it means that you ignore all data where it is close enough to the real data, and you actually decide what is epsilon, depends on the problem. If the error is outside this, then I compute the error as the absolute value of RT minus F minus epsilon. Why I put here minus epsilon? Because I want to start the error from zero. So here the minimum is epsilon, so epsilon minus epsilon is zero. And then I can build the optimum weight in this case based on this error function. Based on this error function, we can build the optimum weight. Then we can get what is known as regression based on kernel machines. It has some features as well. However, that generally the mean square error based regression, as we saw in the second part of this course, is much more like applied, especially when your data is distributed, like normally distributed, or a trend, or tends to be Gaussian distributed multivariate data. Okay, So also yes, that's all about this part. In part 7 is about support vector machine, is important parts of machine learning algorithms. Okay, don't think that machine learning algorithms are only deep learning and tension based learning and neural network. No, all these algorithms are important. Many of them, they are used in in hybrid way. So when you become like expert in machine learning in company, working in company, data scientist working with data, for example, then you who decide which techniques that you can use based on your experience, because you will have accumulated experience that okay, this data is large data, and if I put it in deep learning algorithm, it might not work as it's supposed to be, because deep learning algorithm is a black box, and I will not have I will have very limited capability to understand what is going on. Even it works fine, because deep learning usually can classify very complex patterns, but the problem that you cannot explain why it works in this way. So maybe as a data scientist, you start to think about support vector machine, and then you will get finite, maybe 20, 30, maybe 1%, maybe less, much less than 1%, maybe 0.1%, which means that 1 per thousand of your data as support data. And once you got those as a support data, then you can start study those vectors, why those are the support, why those are on the margin between these two classes. Looking to those, you can build some knowledge, and you can utilize this knowledge to get much more than what machine learning can give you. So the support vector machine is important, and it is good that to be familiarized with it. Um, I didn't put like design software for this, or me myself, I didn't write software for the support vector machine. If it is easy to write, there are many functions there. Yesterday I added one based on the question or request. So I wrote code for the expectation maximization algorithm. And if you are interested in those algorithms that I give in this course, please try to build your own function. Simulate every function that we give in this course. This is the only way that you guarantee for yourself that you understood it deeply. Even you understand the math behind every algorithm, if you didn't like simulate it yourself, or didn't write a code to work with this algorithm, you cannot guarantee that you understood it very well. So try to build your own function, even not necessarily that you will use it later, because as I said, it is better to use those ready functions in Python, for example, because they are very well optimized in terms of speed and memory and everything. However, if you build your own function using any language that you are familiar with, so it gives you deep understanding how the code work. There is another benefit actually if you want to modify the code. Sometimes when you are working in like in big company, or sorry, or with your own company, sometimes you have complicated data and you want to do something with this data that it is not feasible how to do it with the ready functions in Python, or in Julia, or in MATLAB. Even those functions are like open source, but me, at least I'm talking about myself. If you give me code, written code, like 100 line, even I can understand every line, but not necessarily that I understand how the person who wrote this code, how he or she was thinking, the way of thinking. We think in different ways. The way of thinking that for everyone is somehow personal. Okay, so I do like to write my own code, and because I write I can write it in the way that I understood the problem. Even sometimes I am not like that expert in coding, that I can make it like optimize it in terms of memory and execution time and blah blah blah. I'm not that skillful in these techniques. However, when I write my own code, I become like confidence that I now understand, especially when it works, and then I become happy that I now understand it in deeply how it works, step by step. Okay, that's all. Thank you very much, and I open the platform for you. If you want to ask questions, please write your questions on the chat.